Welcome to Full Spectrum Science. I'm your host, Ron Hipschman. Let's talk about solar eclipses. Many people have seen partial eclipses, but very few have experienced the grandeur of a total solar eclipse like you see here. A solar eclipse happens when the moon passes between the sun and Earth. Sounds simple, but there are a few factors we need to consider. First, let's get some perspective about the sizes and distances of the Sun, Moon, and Earth. The Earth is 3.6 times the size of the Moon. Placed on the same slide, the sizes look like this. However, we don't have the distance between the Earth and the Moon shown properly. To do that, we have to change the scale a bit. Now you can see why it's not practical to have both the size and distances scaled properly in books and illustrations. The Moon is, on the average, 240,000 miles from the Earth. That's about 30 Earth diameters between them. I can show you the relative sizes of the Sun and Earth, but I can't space them apart properly on the screen. The Earth is about 1/100th the diameter of the Sun, and it orbits over 100 solar diameters from the Sun. Let's try to make a scale model again. If the Sun were the size of a regulation basketball, 9.5 inches in diameter, the Earth would be a minuscule dot, about the size of a candy sprinkle, less than 1/10 of an inch in diameter, orbiting 85 feet from the basketball. The Earth is invisibly small on this slide, less than a pixel in diameter. Well, that's why they call it space. Eclipses are all about shadows, so I think it's important to take a look at them. Let's state the obvious here. The sizes and distances of the Sun, Moon, and Earth in these diagrams are wildly out of scale and are made this way to demonstrate the phenomena we're discussing. The Sun gives off light from every point on its surface, and this light moves out in all directions. But let's simplify that a bit and look only at extremes. For example, look at light coming from just the top of the Sun. We'll put a light bulb there to represent this. Light passing the Moon is blocked and casts a shadow. Anyone in this shadow cannot see the light bulb. Now, let's look at the other side of the Sun. If we place a light bulb on the bottom of the Sun, light from this bulb will also be blocked by the Moon and cast a shadow of its own. Notice there is a darker shadow where the Moon is blocking the light from both the top and the bottom of the Sun. This is called the umbra. From the lighter parts of the shadow, you can still see the light bulbs, meaning the Sun, peeking out either above or below the Moon. This lighter, partial shadow is called the penumbra. In reality, there are light bulbs all over the Sun's surface, but that doesn't change the diagram since we looked at extremes. Notice that the umbra only touches the Earth in a very small circle I've marked in yellow. You must be within this circle to see the Sun completely blocked out and experience a total solar eclipse. If you're in the penumbra, you'll be able to see some of the Sun peeking above or below the Moon, and you'll experience a partial eclipse. Now, let's look at an annular eclipse, in which the Moon appears too small to cover the Sun. Watch carefully and observe what changes. In an annular eclipse, the Moon is a little further away in its orbit around the Earth. More on that in a bit. Notice that the umbra does not quite reach all the way to the Earth. Under that umbral point, in this area, you're still in a partial shadow and will be able to see both the top and bottom of the Sun peeking around the edges of the Moon. Because the Moon is now further away, it appears smaller in the sky and cannot completely cover the Sun. We see a ring of sunlight surrounding the dark disk of the Moon. This part of the shadow is called the anteumbra. Well, if eclipses happen when the Moon is between the Earth and the Sun, at new moon, then why don't we have an eclipse every month at new moon? The Sun follows a path in the sky called the ecliptic. The sun takes 1 year to complete a circle around the sky. Note this is just a reflection of the Earth's motion around the sun, not the motion of the sun itself. The moon's orbit is tilted 5 degrees to the ecliptic. The sun and moon are only 1/2 of a degree in diameter as seen from the Earth. This means that most of the time, when the moon passes between us and the sun, it will pass above or below the sun's disk. Here, we see the motion of the sun and moon a month before an eclipse. See how it misses? For an eclipse to occur, both the sun and the moon must arrive at both orbits' crossing point at the same time. This point is called the node. Only then can the moon block the sun. Here we see the motion of the sun and moon the month following the one in the previous slide. They both arrive at the node at the same time, and we see an eclipse. Here's a closer view. This is, of course, sped up. Here, we're seeing an annular eclipse. As the moon orbits the Earth, it casts a shadow that moves across the face of the Earth. Here, you see the shadow from the 2017 Great American Eclipse. Notice that the umbra is tracing a red path behind it. You must be inside that red line, inside the path of the umbra, to see a total eclipse. Outside the line, you'd see only a partial eclipse. And here's what it actually looked like from NASA's GOES 16 satellite. We've briefly touched on this, but there are actually 3 types of solar eclipses for you to observe. This is a partial eclipse. You aren't on the path of the umbra center line of this eclipse and only see part of the sun covered. Many people have seen this type of eclipse. In an annular eclipse, you're on the center line, but the moon is too far from the Earth, or the Earth is too close to the sun, or both, and the moon's disk cannot block the entire solar disk. The moon leaves a ring or annulus of the sun showing. The last and most spectacular type of eclipse is the total solar eclipse. Here, the moon can cover the entire disk of the sun, and we see all the special effects the sun has to offer. The diamond ring, Bailey's beads, the corona, and an eerie darkness in the middle of the day. What portion of eclipses are partial, annular, or total? It might be interesting to take a quick look at that. We'll use 5,000 years of eclipses from 2000 BCE to 3000 CE. About 1/3 of all eclipses are partial. Another 1/3 are annular, and slightly over 1/4 are total. There's an additional type of eclipse here called a hybrid eclipse. It's one that starts out or ends as an annular eclipse with a central total eclipse portion. Those make up about 5% of all eclipses. You may have heard people talk about contact times, first contact to fourth contact. Let's quickly go over that. First contact is when the moon first starts to cover the face of the sun. I've momentarily brightened the moon so we can see it, but it's really invisible since we're looking at the dark side of the moon against the blinding surface of the sun. Second contact occurs when the moon just fully blocks the bright surface of the sun. This is the start of totality. Third contact, a few minutes later, is the point when the moon is about to start exiting the solar disk and the total phase ends. Finally, we arrive at fourth contact when the moon fully leaves the sun's surface. I've once again artificially brightened the moon to make it visible. It then happily continues along its way, and the eclipse is over. Let's get back to the annular eclipse. Why do we see these sometimes? The moon's orbit around the Earth is not a circle, it's an ellipse. As the moon orbits, it's sometimes further from the Earth, called an apogee, and then about 2 weeks later, it's closer to the Earth at perigee. The moon is 45,000 kilometers closer at perigee than at apogee. That's almost a 12% difference in distance and hence size we see in the sky. So in the course of 1 month, the moon will grow and shrink. Here, you see the biggest and smallest the moon gets. Let's split the moons and shove them together to make the comparison easier. As you can see, there's quite a difference. Likewise, the Earth's orbit around the Sun is also an ellipse. As the Earth orbits the Sun, it's sometimes farther from the Sun, called aphelion, and then, about 6 months later, it's closer to the Sun at perihelion. The Sun is 5 million kilometers closer at perihelion than at aphelion. Like the Moon, in the course of 1 year, the Sun will grow and shrink because of the Earth's elliptical orbit. Here, you see actual photos of the Sun at the biggest and smallest in the sky. Again, let's split the suns and shove them together to make the comparison easier. There's less difference than the Moon, only 3.3% difference with the Sun, because our distance doesn't really change that much percentage-wise. This is a good thing since we really don't want wide temperature changes on the Earth between perihelion and aphelion. Now, what does all this have to do with solar eclipses? At this point in Earth's history, the apparent size of the moon in the Earth's sky is almost exactly the same as the Sun. This means at certain times of the year, when all three are in alignment, the moon can just barely cover the Sun with only a little to spare. But even today, if the moon is near apogee, farther from the Earth, it looks smaller in the sky. Also, if the Earth is near perihelion, so the Sun looks larger, you won't get a total solar eclipse. The moon won't be able to completely cover the Sun, and we'd see an annular eclipse. The word annular comes from the Latin annularis, or ring-shaped. Before we get to how to view the Sun safely, an important question is, what is there to see? There are many ways to look at the Sun. Here's the Sun seen in visible light, assuming you could dim it enough to observe the surface. Notice the dark sunspots. They're slightly cooler regions of the Sun. They're usually larger than the entire planet Earth. By the way, this is a time lapse. The Sun really takes about 30 days to rotate on its axis once. If you looked at the Sun in the red light given off by hydrogen, you'd get a different picture, telling you a whole new set of information. In the visible violet light of the element calcium, you learn even more. With spacecraft above the atmosphere, you can observe the Sun in extreme ultraviolet. This view was taken from the Solar Dynamics Observatory, or SDO. This X-ray view of the Sun is a combination of 3 different satellite views. Each type of light tells us something different about our star, the Sun. How do we observe the Sun and not harm our eyes? We don't have to worry about X-rays or extreme ultraviolet on the surface of the Earth, since those are filtered by our atmosphere. But we do have to worry about the intense visible and infrared light that does make it through the atmosphere. The easiest and cheapest way of viewing the Sun safely is by using a pinhole. Here, we see Julie holding up a piece of pegboard. What you see on the screen is that each pinhole has produced a small image of the sun. The smaller the pinhole, the sharper, but dimmer, the solar image becomes. You can use your spaghetti strainer, often called a colander. Again, each hole produces an image of the sun. You can even make pinholes by crossing your fingers at right angles. Here's another example using only your hands. So far, all these were taken at the 2017 Great American Eclipse. A good leafy tree can also provide eclipse images as the sunlight filters through holes in the foliage. And another example of pinhole images through trees taken at the Maker Faire in San Mateo, California. If you take a small mirror and reflect sunlight, the mirror also acts as a reflective pinhole. The size of the mirror and the distance to the image matters. If you insist on directly viewing the sun with your eyes, be sure to use an approved solar viewer, which comes in several different configurations. Read the instructions printed on the viewer and follow them. Eclipses are amazing events, but not worth damaging your eyes. Be sure the filter is ISO 12312-2 or CE certified. These folks are looking through welder's glass. You must use number 14 density filters, which reduce the sun's light by a factor of 270,000. Do not use filters designed for brazing. They allow through too much light. A good rule of thumb, if the sun looks too bright, it is. Don't use that filter. You may have heard that you can use fully exposed and developed film, but we advise against this as it depends on many factors and could easily lead to eye damage. The same goes for smoked glass. Never use sunglasses either. They do not filter enough light. Use only filters that are specifically made to observe the sun. We can't stress this strongly enough. You can use a small telescope or binocular to project an image of the sun on a screen, as you see here. Do not look through the telescope or the binocular. Only look at the projection on the screen. If you use a binocular, only use one of the two lenses. Block the other. Also, be aware that you could ruin your eyepiece with the concentrated sunlight passing through it. Here's a closer view of a binocular projection. It's sharper and brighter than a pinhole projection. This is a specialized solar viewer called a sun spotter. Again, this uses safe projection onto a screen. Some older telescopes you may find in your attic came with a solar filter you screwed into the eyepiece. These are very dangerous. The concentrated sunlight passes into the filter where most of it is absorbed. This filter can heat up to very high temperatures and shatter while you're observing through it, causing instant and permanent damage to your eye. Throw it away and use the projection method instead. During a partial eclipse, you must use all precautions when observing the sun. You may never look at the sun without the aid of filters. Similarly, since the sun's bright surface is also visible during all parts of an annular eclipse, you must use all the same precautions when observing the sun. Never look at the sun during an annular eclipse without the aid of filters or using the projection method. During a total eclipse, you still have to use filters or projection during all the partial phases leading up to totality. Only during totality is it safe to use your naked eyes. Here, you see the diamond ring effect as the last bit of the sun disappears behind the moon. A few seconds later, light shining through the mountains and valleys on the edge of the moon breaks up into a series of uneven pieces called Bailey's beads, named after Francis Bailey, even though they were first observed by Edmund Halley. Yes, the comet guy. Close to the sun, you'll see the corona and maybe some crimson prominences, giant eruptions of hydrogen gas above the sun's surface, many times the size of the Earth. The corona, or outer atmosphere, extends outward from the sun. In this longer exposure, you can see it extends out quite far. As soon as the sun peeks out from behind the moon in another diamond ring effect, you must once again use your filter or projection methods to view the rest of the eclipse. Do not damage your eyes. Sometimes clouds form after eclipses because the air gets a bit colder and the water in the atmosphere condenses. You can see a partial eclipse through the clouds sometimes. The last thing I'd like to mention is you can see an eclipse from space, too, now that we have spacecraft orbiting the Earth. Here's a photo of the umbra during a total solar eclipse taken from the Russian Mir space station on August 11, 1999. Here we see several shots of eclipses caught by the Discover spacecraft as it observes the Earth from 1 million miles away. Here is the 2020 South American eclipse as seen by the GOES-16 weather satellite. And from the European Meteosat weather satellite, here's the total eclipse of March 29, 2006. This is a somewhat extreme eclipse of the sun. It was caught by the Stereo spacecraft, which trails the Earth in our orbit. The spacecraft was about 1 million miles from Earth, so the moon looks much smaller compared to the sun. I suppose one could call this an annular eclipse. Thank you for watching this full spectrum science presentation all about eclipses. I'm your host, Ron Hipschman.